In the first part of chapter 14, we looked at two derivatives, the derivative of f with respect to x and the derivative of f with respect to y. And both of these give you rates of change if you want to move in the x direction or the y direction. But what if you want to move in some other direction that's not just parallel to the x-axis or parallel to the y-axis? Then what we're going to need is a directional derivative and an associated tool called the gradient. Here's the setup, and you have to be very careful about thinking about which space you're living in. So first, imagine that you want to move in the direction indicated by the unit vector u equals u1i plus u2j. So notice that this vector lives in the xy plane. So this is a vector that's somewhere down here in the xy plane. And it denotes the direction that you want to move, but you're moving not in the xy plane, but on the surface in 3 space. So that is, you move in the direction of this vector, but it's sort of your shadow as you move along the surface. Okay, you are not in the xy plane, only your direction vector is. So then, your rate of change on the surface, on this surface, given by f of xy, in the direction of u, which is indicated in the xy plane, at some particular point, so maybe there's a point there, a, b, f of a, b, is given by this derivative. So notice it looks very much the same as the derivative f with respect to x and the derivative with respect to y. The difference is that both the x and the y components are moving. So this expression is pretty messy and not really very tractable to evaluate directly. So in the next slide we're going to think about how to actually calculate this directional derivative. So here I'm going to outline the idea behind finding a directional derivative. If you're interested in more details, look on page 744 to 745 of the textbook, and I'd be more than happy to answer questions about those if you're interested. So here's roughly the idea. You're moving in a direction, but it's not necessarily just in the x direction or just in the y direction. But if the component of your motion in the x direction has a rate of change of the derivative with respect to x, and you move a distance given by u1, that component that was in the unit direction vector moving in the x direction. And similarly, when the component of your motion in the y direction has a rate of change given by the derivative with respect to y, and you move a distance u2, which was the component given by the unit vector giving the direction. So here, let me remind you what the direction vector was. It was u1i plus u2j. And so that's where this u1 and this u2 come from. Okay, so if you take those two components of motion together, in the x direction, your net effect is f sub x times u sub 1, plus your contribution in the y direction, f sub y times u sub 2. So the value of the directional derivative is given by f sub x u1 plus f sub y u2. These are the partial derivatives with respect to x and y. And then on this next line we're going to do something a little clever. We're going to sort of undot product this scalar value. So we can write this scalar value as the dot product of two vectors. One is just the direction vector u1i plus u2j. The other one is this new vector that I need. It's the partial derivative with respect to x, I, vector I, plus the partial derivative with respect to y, vector j. And when we dot those together, we get the value of the directional derivative. And let me emphasize that this is, when you plug in values, a scalar, not a vector, which you can see since we're taking a dot product. This particular vector turns out to be of interest quite a lot, and so we give it a name. It's called the gradient of f. Sometimes this is written with an upside down triangle read del f dot u. Let's do an example. So we want to just find the gradient vector of this particular function sine of x squared plus y squared. So the gradient of this function z is the partial of z with respect to x times the unit vector I plus the partial with respect to y times the unit vector j. So all we need to do is find these two partial derivatives. So the partial derivative with respect to x is cosine of x squared plus y squared times the derivative of the inside with respect to x, so that's times 2x, all that times the unit vector I, plus the partial with respect to y, which of course will look very similar. So let's see, we get cosine of x squared plus y squared times the derivative of the inside using the chain rule is 2y, all that times j. And there's the gradient. And notice it's indeed a vector. So here's another example, and this time we'll calculate what we started with, the directional derivative for this function, sine of 2x minus y, in the direction of the unit vector 3i minus 4j over 5. So notice this vector is already a unit vector. If you were given a direction that wasn't a unit vector, you'd first need to normalize that vector. Okay, so first let's find the gradient in general, and then we'll point in or plug in the desired point. So the gradient of f, I need to take the partial with respect to x of f, so that's cosine of 2x minus y, times the derivative of the inside with respect to x, which is 2, times the vector I, plus the derivative with respect to y, so that's cosine of 2x minus y, times the derivative of the inside, which is minus 1, j, and then we're going to take that whole gradient vector and dot that with the unit vector, so that's 3/5 I minus 4/5 j. Okay, so now we just have to do this slightly messy dot product, but it's not too bad. So let's see if I can do this correctly. We get 6/5 cosine of 2x minus y minus, a minus and a minus, so that's plus 4/5 cosine of 2x minus y. Hopefully I did that correctly. And notice that the vectors are gone. This directional derivative is not a vector, it's a scalar. And so finally, the question asked me to evaluate this directional derivative at the point 1, 2. So let's do that quickly. So this directional derivative evaluated at the point 1, 2, I'm just going to plug in 1 and 2. And let's see, 2 times 1 is 2, minus 2 is 0. So this is cosine of 0, which is 1. And so in the end we get 6/5 plus 4/5, which is 10/5, or 2. That's a plus. Okay, so let's briefly talk about some interpretations of the gradient vector, and we'll discuss more about this in class. So remember that the directional derivative is given by the dot product of the gradient of f and the unit vector, which gives the direction. So the geometric definition of this dot product says that I calculate this directional derivative by taking the magnitude of the gradient of f times the magnitude of the unit vector, which is 1, times the cosine of the angle between those two vectors. So in this bottom line, I've just taken out this factor because its value is 1. So notice that cosine of theta is biggest when cosine of theta is equal to minus 1. So cosine theta, or I'm sorry, not minus 1, cosine 1 is the biggest that this could be. And so When that happens, I get the biggest value that the directional derivative could have. And so I get a couple things. So first of all, if I think about the gradient vector, it points in a particular direction. And it points in the direction of the greatest rate of growth on the surface that I'm interested in. So if I want to climb as steeply as possible, I should move in the direction indicated by the gradient vector. Keep remembering that this gradient vector lives in the xy plane, whereas the surface lives in 3 space. Okay, 2 others. That the value of that maximum rate of change of f is in fact the magnitude of the gradient. And finally, it's not too hard to see that the gradient vector will always be perpendicular to contours. We talked about that a little while ago.